units of rate of reactions or rate constant. From units of rate constant K, we can find out order of reaction. Suppose this is a common reaction, A plus B gives products. Now differential rate law for this reaction will be minus dA by dt, which is initial rate of reaction, is equal to K concentration of A raised to small a, concentration of B raised to small b, where K is rate constant, concentration of A means initial concentration of A, concentration of B, initial concentration of B, small a, order of reaction of A, small b, order of reaction of B. Now, unit of initial rate of reaction is moles per liter into 1 upon time. Concentration will be moles per liter. So, for A we write moles per liter raised to small a, for B we write moles per liter raised to small b, and K is rate constant. So, K is equal to moles per liter raised to A plus B. Now, change the side of moles per liter. So, we can take it on the left hand side. So, now we will make K as a subject. So, K is equal to liter per mole raised to A plus B into moles per liter raised to 1 into 1 upon time. So, moles per liter can be cancelled. Therefore, K is equal to liter per mole raised to A plus B minus 1 into 1 upon time. So, if A plus B is net order of reaction, for example, A plus B is 0, then unit of K will be moles per liter per time. That is 0 order reaction. If A plus B is 1, then it is called first order reaction, and for that unit will be time inverse. If order of reaction is 2, that is second order reaction, then unit of K will be liter per mole per time. If A plus B is equal to 3, then it is third order reaction, then unit will be liter square mole raised to minus 2 time inverse. Thus, for any order of reaction n, for nth order reaction, we can write common formula of unit of K, which is liter raised to n minus 1 mole raised to 1 minus n time inverse. Now find out order of reaction. This reaction is given to you. Differential rate law for this reaction is rate is equal to K NO raised to 2. So here power of NO is 2, therefore it is second order reaction. H2O2 plus 3I minus plus 2H plus gives 2H2O plus I3 minus 1. For this differential rate law is rate is equal to K H2O2 raised to 1 I minus raised to 1. That means net order of reaction is 1 plus 1, 2. Here H plus has no power. That means the order of reaction of H plus will be 0. Next, CH3CHO on decomposition gives methane plus carbon monoxide. For this, rate is equal to K CH3CHO raised to 1.5. That means order of reaction is 1.5 or 3 by 2. Next, chloroform reacts with chlorine and you will get carbon tetrachloride plus HCl. Differential rate law for this reaction is rate is equal to K CHCl3 raised to 1 Cl2 raised to half. So order of reaction of chloroform with respect to chloroform is 1 and with respect to chlorine is half. Net order of reaction is 1.5. C2H5Cl gives C2H4 plus HCl. For this, rate is equal to K C2H5Cl raised to 1. That means this is first order reaction. So if you are given differential rate law for any chemical reaction, then from this differential rate law, we can find out order of reaction. Or if you are given unit of rate constant K, from these also we can find out order of reaction. For example, the first one where the order of reaction is 2, so the unit of K will be liter per mole inverse per time inverse. Here also order of reaction is 2, so liter per mole inverse per time inverse. So this way for any chemical reaction, you can find out order of reaction only if differential rate law is given or unit of K is given. Now we'll take some example of photochemical reaction. Hydrogen reacts with chlorine only in presence of light and it gives HCl. Now for this reaction, rate is equal to, that is differential rate law is equal to K H2 raised to small a Cl2 raised to small b. Now in this reaction, at any time, if you change concentration of hydrogen, it is not going to affect the rate of reaction. If you change the concentration of chlorine, it is also not affecting rate of reaction. But if you change the intensity of light, then and then rate of reaction changes. That means this reaction occurs due to light. Such reaction, that means this reaction occurs due to light. Such reaction is known as photochemical reaction. So as concentration of hydrogen cannot change the rate of reaction, so order of reaction of hydrogen is 0. Concentration of chlorine cannot change the rate of reaction, therefore order of chlorine is also 0. Therefore, rate is equal to K and A plus B is 0. It is known as zero order reaction. So all photochemical reactions are zero order reactions. Some elementary reactions. Elementary reactions means molecularity of this reaction is 1 plus 1, 2. So it is bimolecular reaction. Now differential rate law for this reaction is rate is equal to K H2 raised to 1 I2 raised to 1. That means net order of reaction is also 2. So if molecularity and order of reactions are same, then such reaction is known as elementary reaction. They are very simple reaction. Some complex reactions. For example, hydrogen reacts with bromine and gives HBr, where molecularity of this reaction is 1 plus 1, 2. But it is the order of reaction is not 1 plus 1 is equal to 2. In the beginning, there is no HBr. So in absence of HBr, differential rate law, that is initial rate is equal to K H2 raised to 1 Br2 raised to half. That means net order of reaction is 1 plus 0.5, which is 1.5. But once the reaction starts, the order of reaction changes because this reaction occurs in 5 different steps. For example, first step, bromine reacts and produce bromine free radicals. So for this, rate constant say K1. Second step, hydrogen reacts with bromine free radical and produce HBr plus hydrogen free radical. For this, rate constant is K2. Now hydrogen free radical reacts with bromine again and produce HBr plus bromine free radical. Rate constant is K3. Fourth step, hydrogen free radical also react with HBr and produce H2 plus bromine free radical. Rate constant K4. Last step, bromine free radical reacts with bromine free radical and produce bromine. So K5, that is rate constant. Now, if we want to write for HBR, production of HBR, differential rate law of HBR, then dHBR upon dt is equal to, see, in this two reaction, HBR is product, so this two will be positive. In the fourth reaction, HBR is reactant, so this will be negative. So we write K2 into H2 into Br dot plus K3 into H dot into Br2 minus K4 into H dot into HBR. Similarly, this is equation 1. Similarly, for bromine free radical, we write differential rate law dBr dBr dot upon dt is equal to K1 Br2, because in this reaction bromine dot are products. In second reaction it is reactant. In fifth reaction also Br dot is reactant, while in case of third and fourth these are products. So we will add K3 and K4. So K3 H dot Br2 plus K4 H dot HBr minus K2 H2 into Br dot minus Br dot K5 Br dot square. Now bromine free radical at the end of reaction is not existing. Therefore this will be 0. So it is equal to 0. So we can change the side of this two. Now for these 5 reactions we'll take differential rate law of H free radical. And H free radical is in second reaction, third reaction and fourth reaction. So dH dot upon dt is equal to K2 H2 into Br dot minus K3 H dot Br2 minus K4 H dot HBr. This is equation 3, and as H dot is not existing at the end, this is equal to 0. Now we can change side of this two also. So dBr dot for second second equation, we write K1 Br2 plus K3 H dot Br2 plus K4 H dot HBr is equal to K2 H2 Br dot plus K5 Br dot square. For this reaction, from equation 3, we can write K2 H2 Br dot is equal to K3 H dot Br2 plus K4 H dot HBr. Now we add these two equations. Then we can have K1 Br2 is equal to K5 Br dot square. Why? Because K3 will be cancelled, K4 is also cancelled, K2 is also cancelled because they are in opposite directions. And therefore K1 Br2 is equal to K5 Br dot whole square. Now Br dot whole square is equal to K1 upon K5 into Br2. So Br dot is equal to root of K1 upon K5 into Br2. Substitute the value of Br dot in equation 3. So instead of Br dot we write K1 upon root K1 upon K5 into Br2. So K2 H2 into root K1 upon K5 Br2 is equal to K3 H dot Br2 plus K4 H dot HBr. Now H dot is common in this two, so we'll keep it outside, and this others will be in bracket. So H dot is into K3 Br2 plus K4 HBr. Now we change the side of this and we can make H dot as a subject. Therefore K2 into under root K1 upon K5 into Br2 into H2 upon K3 Br2 plus K4 HBr. Now this is equation 1, and in this equation we can substitute the value of H, Br dot and H dot. So K2 H2 under root K1 upon K5 into Br2 plus K3 Br2 into K2 under root K1 upon K5 into Br2 into H2 upon K3 Br2 plus K4 HBr minus K4 HBr into K2 under root K1 upon K5 Br2 into H2 upon K3 Br2 plus K4 HBr. Well, if you keep common K2 into H2 under root K1 upon K5 Br2, then we have this equation. And if you simplify this, you will get this formula. Then we have this. And for this, if you take constant Ka, then we can make it more simple formula of this. And K4 upon K3 is equal to Kb. Then we have Ka H2 into Br2 raised to half upon 1 plus Kb into HBr upon Br2. So from this we can find out order of reaction of this reaction. And it is very complicated state. Well, average rate of reaction and instantaneous rate of reaction. For this we write reactants give products. Initial concentration of reactants maximum. Concentration of product in the beginning 0. Final concentration of reactants will be minimum and product will be maximum. So if you draw individual graph for reactants and product, then in the beginning reactant is maximum and with respect to time it is decreasing. Product in the beginning 0, with respect to time it is increasing. Then we can decide any two concentration on this graph, C1 and C2. So we can extend this line and find out T1 and T2. That means time required for this concentration, C1 and C2. Similarly, here you can select two concentrations, C1 and C2, and with respect to this we can find out time T1 and T2. Then T can be any time where you want, at which time you want to find out rate of reaction. Suppose you want to find out rate of reaction or at time T2, then select point where the T2 will intersect this line, your curve, and draw a tangent over there, and then you can draw a slope and find out slope. So from slope we can find out instantaneous rate of reaction. So change in concentration of reactant would be C2 minus C1, that is minus delta C and or minus delta R. Here it is negative because concentration decreases. Change in concentration of product, that is C2 minus C1, that is delta C. Why? Because C2 is greater than C1 or concentration increases. Change in time, delta T, here also delta T. Average rate of reaction would be minus delta C2 minus C1 upon T2 minus T1. Or in this case, average rate of reaction is equal to C2 minus C1 upon T2 minus T1. Or minus delta R upon delta T, here delta P upon delta T. This way, either from the graph of concentration of reactants versus time or concentration of product versus time, we can find out average rate of reaction. To determine the instantaneous rate at any time t, a tangent is drawn. The slope in this part of the curve is equal to the instantaneous rate at that time. So instantaneous rate of reaction is equal to minus slope of reactants, that is minus dr by dt, or for product plus slope of product, that is dp by dt. The following results are obtained in the hydrolysis of chlorobutane. At 0 time, the concentration of chlorobutane is 0.1 molar. After 100 seconds, it is 0.082. After 200 seconds, concentration 0.067. After 300 seconds, concentration of chlorobutane 0.055. After 400 seconds, concentration 0.044. After 700 seconds, concentration is 0.021. After 800 seconds, it is 0.017. So solution. First we'll take time t1 and time t2. So between first and second part, we have 0 and 100. Then 100 and 200. 200 to 300. 300 to 400. 400 to 700. 700 to 800. At that time, concentration would be, initial concentration is 0.1 and final concentration after 100 seconds is 0.082. Similarly, at 100 seconds it is 0.082, at 200 seconds it is 0.067. This way you can write all R1 and R2. Now, delta T will be 100 minus 0, that is 100. This here also 100. Only in this case 700 to 400, that is 300. And R2 minus R1 for all will be minus 0.018, minus 0.015 and like that. As you have R2 minus R1 and T2 minus T1, then you can find out average rate of reaction, that is minus delta R upon delta T. So 1.8 into 10 raised to minus 4. Second set average rate of reaction is 1.5 into 10 raised to minus 4. Between 200 second and 300 second, average rate of reaction is 1.2 into 10 raised to minus 4. Between 300 and 400 seconds, the average rate is 1.1 into 10 raised to minus 4. This way we can find out average rate of reaction. It is apparent from the result that the average rate decreases from 1.8 into 10 raised to minus 4 to 4 into 10 raised to minus 5 moles per liter per second. Well, it is difficult to know instantaneous rate of reaction from these results. To determine the reaction rate at any time, that is instantaneous rate, for which we have to plot a graph of concentration of reactants versus time. Example 1. From the concentration of reactant at different times given below, calculate the average rate of reaction. This is the result. 0 time, at 0 second, concentration of reactant is 160 into 10 raised to minus 3. After 5 seconds, it is 80 into 10 raised to minus 3. After 10 seconds, it is 40 into 10 raised to minus 3. After 20 seconds, it is 10 into 10 raised to minus 3. After 30 seconds, 2.5 into 10 raised to minus 3. So we can use this formula to find out average rate of reaction. So for first step, C1 is equal to 160 into 10 raised to minus 3. C2 would be 18 into 10 raised to minus 3 times 0 and 5. So put these values over here and you will get average rate of reaction between 0 and 5 seconds. Similarly, if you want to find out average rate of reaction between 5 seconds and 10 seconds, use this. 18 into 10 raised to minus 3 C1. C2 would be 40 into 10 raised to minus 3. T1 5 seconds, T2 10 seconds, and that is average rate of reaction. Between 10 and 20 seconds, C1 would be 40 into 10 raised to minus 3. C2 10 into 10 raised to minus 3. Time T1 10 seconds. T2 20 seconds. Substitute and you will get average rate of reaction. And finally, between 20 and 30 seconds, 10 into 10 raised to minus 3, 2.5 into 10 raised to minus 3. So here we have 20 and 30 and you can find out average rate of reaction. And if you will calculate this, the average rate of reaction decreases.